In this video, we're starting by looking at matrices. So introduction to matrices, what are they, what do we use them for, how can they help us? So a matrix, rectangular array of numbers arranged in rows and columns. The numbers in the matrix are called the elements of the matrix. Let's change over to blue. The elements of the matrix. The arrangement of numbers in matrices is an extension of our number system, and the rules that govern matrix calculations have many similarities with the arithmetic of numbers, and we'll be looking a little bit closely at that later. So the matrix below, 2, 0, 1, -4, -1, and 2, is a 3x2 matrix as it has 3 rows and 2 columns. We say the size or order of the matrix is 3x2. So with that matrix, we've got that is a 3x2 matrix, and it always goes row and then column. So row and then column. So in general, if we have a matrix, it's denoted by a capital letter. So we've got capital A there is equal to A1, A2, so on and so forth, all the way to A1n. And then the rows go from A11, A21, all the way to AM1, and then the bottom rightmost element is A of Mn. So this dictates a standard M by N matrix. So if it was 2x2, it would go from A1 to A22. If it was 100 by 100, it'd go from A11 all the way to A100, 100. So we enclose a matrix in square brackets and use capital letters to denote it. The elements of matrix A are referred to as A subscript ij, where I refers to the row position and j refers to the column position. Okay, when the numbers of rows and columns in a matrix are equal, it is called a square matrix, simply by the fact that a square has equal length and width. If a matrix only has one column, we call it either a column matrix or a vector matrix. And that comes from the fact that vectors can be represented as matrices. So if you had something like 2, 1, 3, that could be the same as 2i plus 1j plus 3k. So that's in 3 dimensions. We've only looked at 2 dimensions so far, but you get the idea. If a matrix only has one row, it's called a row matrix. So, in the example below, we want to write the order and type of matrix, and then the A21 and A13 elements. So in our first one, we've got a square matrix, it's 3x3. Our A21 element is in the second row, in the first column, so that's our -4 over here. And our A13 element is in the first row in the third column, so that's -3 over here. Okay, for C, it is a 3x1 matrix. It has 3 rows and 1 column. A21 is -2. And then A13, well, we're looking for what's in the first row and in the third column. Oh, we don't have anything there. So we can't answer that question, right? It's not that it's 0, it's that it doesn't exist. And then for part D, we've got that is 1 row by 2 columns. So that's a 1x2 matrix. And in fact, neither of the elements can be found. So there is no A21 element or an A13 element for matrix D right there. Okay, we have some special matrices as well. So the 0 matrix, also referred to as the null matrix, is a matrix with all elements equal to 0. You'll sometimes see it written as 0 or O, and it just basically means of an appropriate size. Generally, you have to use context clues as to how big this matrix is. Every element inside it is a 0. Another interesting matrix that we use is called the identity matrix. So the identity matrix is always a square matrix with 1s on the leading diagonal and 0s in the other elements. So if we were looking at a 2x2, it would go 1, 0, 0, 1. If we're looking at a 3x3, It would go 1, 0, 0, 0, 1, 0, 0, 0, 1. And that pattern continues depending on how big you make it. Our general form would be 1, 0, and then sort of dots to show that the 0 is gone forever. 1's on the leading diagonal, show that the 1's gone forever, and then also show that the 0 is gone forever there. So that's just make it as big as you need it to be, but it's always going to be square. Okay, equality of matrices. So two matrices are equal if and only if they have the same order and each of the corresponding elements are equal. So if we're told here, A plus 2B, 13C is equal to 4, 2A take B, negative 2, it means all of the corresponding elements are equal. So we can rewrite this as a system of linear equations. So we can read off here that C is just equal to negative 2, and then we have two equations and two unknowns, so we can apply simultaneous equations to the first one. So let's call this equation 1, this equation 2. We don't have a aligning coefficient of either of our variables, so we have to multiply equation 1 by 2. Okay, so now that we have 2a in both of our equations, we can subtract them from each other, and that means that we will no longer have that a term. We'd just be working with b. So if this is equation 3, we'll do equation 3, take equation 2. So that gives us 2a take 2a is 0. We also get 4b take negative b, which is 5b. And then we get 8 take 13, which is negative 5. So we can see from that b is equal to negative 1. If b is equal to negative 1, we can sub back into equation 1. And we find that a minus 2 is equal to 4. So a has to equal 6. So that means our equivalent equations are 4, 13, negative 2. So if you substitute the values into those two matrices that we started with, we'd both get 4, 13, negative 2. Okay, let's start doing some arithmetic with our matrices. So to add and subtract matrices, it can only be done if the matrices are of the same order. So they need to have the same number of rows and columns. And addition/subtraction of matrices is performed by just adding or subtracting the corresponding elements, and it is commutative. So, sorry, I should specify just addition is commutative. That means a plus b is the same thing as b plus a. So just like regular addition, matrix addition also has the commutative property. So let's take a look at some of our sums or differences. So a plus b is the first sum we've been asked to find. So 1, 2, 3, 4 plus 1, 4, 2, 3. All we're doing is adding the individual elements. So I'm going to get 1 plus 1 is 2. 2 plus 4 is 6, 3 plus 2 is 5, and 4 plus 3 is 7. Okay, for part B, we're finding the difference now. Oh, difference. 1, 4, 2, 3. So now instead of adding them, we subtract them, which is the same as adding the negative of it. So 1 add negative 1, or 1 take 1, is 0, 2 take 4 is negative 2, 3 take 2 is 1, and 4 take 3 is negative 1. Okay, and lastly, part C. So we've got B take C is not possible. Why is it not possible? Well, we're trying to take a 2 by 2 away from a 2 by 3. So 2 by 2 cannot be taken away. from a 2 by 3. Right, so when matrices are added together, A plus B, and they equal the null matrix, matrix B is what we call the additive inverse. So just like in arithmetic, if I were to say 2 plus what equals 0, you'd say, oh, -2. 2 plus -2 is 0. We have a similar process for matrices. We call it the additive inverse, and it's going to be taking your matrix and multiplying everything by -1. So, speaking of multiplying by -1, let's talk about multiplication by a scalar. So when a matrix is multiplied by a scalar, each element of the matrix is multiplied by that scalar. So for example, if we have 2 times B take A, we're first going to find the matrix difference between those two matrices. And then the solution that we get, we're going to just multiply each element by 2. So B take A, we've got -5, -3, 3, 4. And then A is 3, 5, 4, 7. So that's going to give us -5 take 3 is -8. -3 take 5 is -8. 3 take 4 is -1. And 4 take 7 is -3. So we then just multiply that matrix by 2. We get -16, -16, -2, -6. So that is part A. For part B, we have that A plus X is equal to the null matrix. So what we have to do is rearrange this to make X the subject. So we find X is O take A. So I've taken A from both sides. A take A on the left-hand side is giving me the null matrix. The null matrix plus anything is itself. So X plus nothing is X. And on the right-hand side, we get the null matrix take A. So that is just as we anticipated, the same as multiplying our original matrix by -1. Okay, and our last one here, we've got B plus 2A take 3I. So B is -5, -3, 3, 4. 2A is going to take the value of A and double it. So we're going to get 6, 10, 8, and 14. And then take 3I is going to take the identity matrix and multiply it by 3. So 3, 0, 0, 3. And what we're going to get with that is X is equal to, I'm going to make a bigger matrix here to actually show my addition. So -5 plus 6, take 3. 3 plus 8, take 0. -3 plus 10, take 0. And 4 plus 14, take 3. And what that leaves us with is -2, 7, 11, and 15. Okay, example 4. Given A, B, and C, determine the values of X and Y if X times A plus 2B is equal to C. This is the last example for this video. What we're going to want to do is distribute that X to both terms of our A, so that becomes 3X, -5x. We're adding to it 2b, so we're adding -10, 8. And that is going to equal to 2y. So, reminder, the elements of the matrix have to equal each other, so we get 3x take 10 is equal to 2, and -5x plus 8 is equal to y. So this first equation only has one variable, so we can quite easily solve that. So 3x, we add 10 to both sides, that's equal to 12. X is just equal to 4. Substitute that back into our other equation, we get y equals -20 plus 8, which is just equal to -12. So there's some early applications of matrices. How can we use it in terms of adding, multiplying by scalar vectors, and subtracting, and how that can be useful for us. In the next video, we'll be looking at multiplying matrices. Thank you.